So some of these are ionic. I went ahead and put check marks beside the ones that are ionic over here. And like the NaCl and the Al2O3, remember the ionic stuff is going to be something in the positive part of the chart, which runs all the way over the stair steps, with something in the negative part of the chart, so over in there. So that's going to be ionic. So NaCl and Al2O3, they both fall into those categories. If you jump down to the bottom, the Mg, it actually falls over here, and this is a negative polyatomic group. So the ionic halfway applies on this one also. So for the ionics, you just go with their charges. So the Na is in the first column. It's in this column right here, so it's +1. Now, notice that we're talking about oxidation numbers, not charges, but it will be the one that wants to lose the electron. So, and then the chlorine, it's over here, and this isn't well drawn because that's supposed to be the last column, but it's the -1, and so that's -1. And then for the Al, it's going to be over in this section right there, and so it's actually going to be +3. And then the oxygen is 1 over, and it's going to be the -2. You can look at an actual real periodic chart to really see how the columns line up. Now, we're going to be moving on over and looking at things that are basically alone. So the ones that are alone, these two, without a charge, like they have a charge that's neutral, then their values are just 0 and 0. And the one that's alone and has a charge, it's its charge. So those are like all not hard. Like there's nothing really new about that. You would probably go ahead and go with those values anyways. Where things get a little squirrely is right over here, and it's where you have things like the O and the F, like they both are over on this side of the chart, N is over on this side of the chart. So those are two covalent things. So if you're trying to think of, well, which one's going to want to lose the electron, covalent things tend to want to share. So we do know that these undergo ionic oxidation reduction reactions, and so we know that they do, and so we're just going to look and see, well, which ones would be the ones that would be losing and gaining the electrons. So what you do is you're going to base this on the most electronegative. So fluorine in anything is the most electronegative. That one gets its charge. It's going to do what it wants to do. So that one has to be a -1. And then there are 2 of them, and so times 2. And then you can see that if the whole compound is neutral, which it is, then it means that, like if you put an X here, if you have to see it with an X, X minus 2 equals 0, so X is equal to 2. So that oxygen is not a -2, that is actually a +2 on the oxygen. Then if we go on to the NO section, for the NO, between N and O, N is, it's right, it goes across actually the way I wrote that. So N is to the left of O, so O is more electronegative, so that one's going to get the charge you expect, which is the -2. Nope, it's not letting me write on there. There we go, -2, and there are 2 of those. And the whole thing equals 0. So that would mean, it's kind of like saying I have X. So it would be like saying X minus 4 equals 0, X equals 4. So that is going to have a +4 oxidation state. And then if we go over here, we've got a -2, and there are 3 of them. Notice that oxygen is still more electronegative. It's still the same 2 elements. But notice right here we have a charge. It needs to equal -1. So what number, -6, will give us a -1? So you'll just add 6 to both sides, and that's going to give you 5. So that's the oxidation state of the nitrogen. Now finally, we're going to go ahead and look at these. This right here, because it's ionic, it's just going to be its charge. And this whole group over here is the -3 charge. That's why there are 3 of these, and there's 2 of those. That's how they charge balance. So we're good on the magnesium being what it is. So now we're going to look at the PO4 group. And as a note, all PO4 -3s will come up with the same exact oxidation situation. So phosphorus is actually located under nitrogen. So between the 2 of them, oxygen is still more electronegative. So we have oxygen being -2, and there are 4 of them. And the whole thing has to equal 3. So if we're trying to figure out P's, we'll say X, and then the negative 2 times 4 is -8 equals -3. And so we're going to add 8 to both sides. So we have X equals 5. So the phosphorus is the 5, the oxygen is the 2, and then the magnesium is the +2. And that's how it's going to line up in any kind of a oxidation reduction reaction.